This is part 2 of Unit 1, Lesson 6, Limits and Continuity. In this part of the lesson, we're going to go over some examples that are going to use our properties of limits. So let's just take a second here to look those over. Went over those in part 1. So our properties of continuity is that if we know f and g are continuous at a point C, then the function is also continuous at that same point C with these properties. So you can multiply f or g by a scalar. You can add or subtract g. You can multiply f and g. You can find the quotient of f over g provided that f of c is not equal to 0. And when you do the composition of the functions f of g of x, if g is continuous at c and f is continuous at g of c, then the composition is also continuous at c. So let's do some examples using those properties. So our first example is example 3. It says for c equals -3, 3, and c equals 7, find f of c, the limit as x approaches c from the left of f, the limit as x approaches c from the right of f, and the limit of f as x approaches c. Justify your findings using the 3-point definition of continuous. So what we're going to do then is decide if it's continuous. So let me do this. Let me divide this in half and then down here, because I'm going to need a lot of space for each of these. So let's start with x equals -3. So let's find f of -3. So looking at our graph, f of -3 is 2. It's right here. And then the limit as x approaches -3 from the left is going to be along here. So that is -1. And then the limit as x approaches -3 from the right, it's coming from the other way, is also -1. But we can say, before I get to the but, that the limit as x approaches 3 of f of x, since these two are the same, is going to equal -1. But this is not continuous. At x equals -3, since f of -3 is not equal to the limit as x approaches -3 of f of x. You're going to get, you need to get used to the idea that you're going to have to be this precise when you're talking about continuity. And some of the other concepts we're going to go into, they are going to expect, the AP people are going to expect you to list your criteria based on the definition of why a function is not continuous at a point. So you have to make sure that you can say all this. And so this is just practice leading into that. Okay, so let's try at x equals 3. So at 3, I erase all my markings here at -3. Start over. So at x equals 3, f of 3 is undefined. There's just an open circle there. Just have that big open circle there. The limit as x approaches 3 from the left of f of x is going to be the value where that circle is, which is 1. Whoops, I'm at 5. Hold on. Sorry, we're at 3. Okay, so let's try this again. Here's 3. So f of 3 still does not exist, though, because we're at an infinite limit. So the limit from the left is infinity, and the limit from the right of f of x is also infinite. So the limit itself is an infinite limit, but even though we can say that the limit is positive infinity, it's not a real number. So this is also not continuous. At x equals 3, since there's two reasons actually. F of 3 is not defined, or you could say, you only need to say one if something's not something. Or the other reason you could use is say that the limit is not a real number. You could say that it equals L, which is infinity, which is not a real number. But in this case, it's easier to say that the value of the function doesn't exist. Okay, so let's do the last one at c equals 7. So let's start with f of 7. And I'll erase the graph again. This time I'll make sure I pick the right point. So 6, 7. Okay, so here's 7. So f of 7 is 3. So that's a good start. Then the limit as x approaches 3 from the left would be along this way, and that's going to be the same as the limit, so that's also 3. And then the limit as x approaches 3 from the right, that's going to be here. There we have a problem because that is 6. So the limit as x approaches, why am I putting 3? Sorry guys, I'm having a bit of a brain fart right now. This should be 7 from the left. This is 7 from the right. And so the limit as x approaches 7 does not exist. So now we can say that is not continuous at 7. We have a couple reasons again. Since the limit as x approaches 7 does not exist. Okay, so none of those points that were chosen were points of continuity for that function. Okay, whoops. Did I go too far? I sure did. Okay, next topic, confirming continuity over an interval. So we talked about that. You must be able to confirm continuity without a graph or calculator by using your knowledge of a function's behavior for the parent function and their transformations. So in other words, we know that x squared is continuous. That's the parent function. So a transformation would be x squared plus 3x minus 8. And you'd have to be able to prove from what you know of the parent function and the way the transformations work that the function is still continuous on whatever interval that you're given. So example 4 says, find the values of x where the function is discontinuous. Describe the type, infinite or removable. Justify your answering by using the definition of continuity. Now these questions are more like what you might see as like a part A of a problem. So the first problem is f of x equals 1 over x minus 3. So the first thing we know that it is not continuous, since that's what we're looking at, not continuous at our asymptote, which we can find. X equals 3. Okay, so now we have to usually go into a little more detail. So how can we justify this? And so what we're going to do is we're going to show that the limit is not a real number, or even show that it does not exist. So we have to think in terms of the left and right hand limit. So let's look at those. So if we look at the limit as x approaches 3 from the left of f of x, let's think about a number we would put in. So from the left of 3 would be a number like 2. So if you look at that fraction, you'd have like 1 over 2 minus 3, which is a negative number. So if you do like 2.9, you're still negative. So what we're looking at is this function is staying negative as we approach 3 from the left. So the limit from the left is going to be negative. Now if we use that same argument when we look at the limit as x approaches 3 from the right, we'll use numbers to the right of 3. So let's start with something bigger like 4. So 4 minus 3 is a positive number. And then if we get a little closer, like 3.9, we're still positive. 3.01 minus 3 is still a positive number. So this is, if you're looking at the graph, it was going to look something like this as you're coming from the right. So this is going to be positive infinity. Okay, so we know that's true. And then we can also say that f of 3 does not exist. And we can put a little note here that the limit as x approaches 3 does not exist. So that's how you justify your answer using the definition. We showed that there's no limit and f of 3 does not exist. Okay, so the next one, don't jump to do exactly what you did for A, because you want to make sure that you've simplified as much as possible. Because what we're going to see here is that the numerator factors and we actually don't have an infinite discontinuity there. So we're looking at a line with a hole in it. And that hole is going to be at that denominator point, which is -2. Okay? Now remember, at this point, this type of question, you're not going to have your graphing calculator. But if you wanted to put the original function in your calculator right now, just to verify that, you can. But that's what we're going to be looking at. Okay, so now we're going to find the limit as x approaches 2 of g of x. That's now, we can substitute 2 in, because now it's just a hole. We don't have to worry about an infinite limit. And remember, it's about approaching. So that's going to be 7. And we also know, though, that g of 2 doesn't exist because in our original function, x cannot equal 2. I'm sorry. Let me start this over again. It's not 2. I apologize. We're at -2. All right, so let me start this over again. So the limit as x approaches -2 of g of x, let me put -2 in this time, we're going to get -1. Okay. And we can say, but g of -2 does not exist. Therefore, g of x is not continuous at x equals -2. I apologize for that. I did not have -2 on my paper that I'm referring to, and so I made a mistake. Okay, so next example. So removing discontinuities. So use the definition of continuity to find the value of k so the function is continuous for all real numbers. So the College Boards likes problems like this to see if this is a way for them to get at whether or not you really understand the definition of continuity. So we're going to have to use the 3 parts of the definition of continuity at a point. So we're going to have to use the idea that the left and right hand limits exist, that they equal each other, that the value of the function exists, and it equals the value of the limit. So here's what we know. We know that we're looking at the, whoops, forgot to pick my pen. We're looking at the point 2. So we're going to take the limit as x approaches 2 from the left of g of x. And we know that has to equal the limit as x approaches 2 from the right of g of x. So in other words, since this is a polynomial piecewise function, we can substitute. So what we know is that kx squared, because that's what we would substitute into, has to equal kx minus 6. And so with this in mind, we can solve this then. So we have kx squared minus kx plus 6 equals 0. And we know that x is 2, so we have k times 2 squared minus k times 2 plus 6. And then we can solve this for k. So 2k equals negative 6, so you get k equals negative 3. So now we know we can find everything we need about this function now that we know that what k is. So the limit, let me use a different color, as x approaches 2 of g of x, if I substitute negative 3 in, is going to be, and I'll just do negative 3 times 2 squared, and I get negative 12. So then g of 2 has to equal negative 12. And g is continuous. All right, next example. Now we have h of x. So we have a piecewise function again. So here's what we know, because k is only in the one piece, and we see that our break here is at 4, so we're going to use that. So the limit, we can find the limit from the left right away because we don't have a k in there. The limit as x approaches 4 from the left of h of x is going to equal the absolute value of, let's not do a direct substitution here. Let's kind of think about what's going to happen. You're going to have, these two are going to be exactly the same because you can't put 4 in here because the denominator will be 0. But think about, let's say we put 3.9 in there. You'd have like the absolute value of 3.9 minus 4 over 3.9 minus 4. So you're going to have a positive number over a negative number, but they're going to be the exact same number. So this is going to always equal negative 1 from the left. You can make the number smaller, like you could do 3.999, not smaller, but closer to 4, 3.999. But you're still going to have the same positive number over the same negative number. All right, so what we can use this now, because if we say that the limit as x approaches 4 from the right of h of x, we know that has to equal negative 1. And we know that that has to be equal to what we get when we substitute in our right piece of the function, which is 5k minus 4 times 4, because that's what we're substituting in, because we can substitute in this piece. And then we can solve this for k. So we have negative 1 equals 5k minus 16. 5k equals 15, so k equals 3. And so that we can say that the limit as x approaches 4 of h of x has to equal that negative 1. And h of 4 has to equal negative 1. So h of x is continuous. Okay, example 5. How much more do we have? I think I might continue this. Well, I'm pretty close. Let me just finish this up in this video. I know it's going to be a little long. I apologize. So example 5 is given this 3-piece function. For what values of x is h of x not continuous? Justify. Okay, so what we want to look at first is the fact that all 3 of these pieces are continuous functions on their own. So you have a line that's continuous everywhere. So every point less than negative 2 to be continuous. You have a horizontal line or a point right at 3. So that's continuous because it's a point. and then you have a cubic function for x is greater than -2. So that's going to be continuous there. So what we have to look at is what happens when you join together. So what we want to do is we want to use the criteria for continuity. Come on, there we go. Okay, so first thing we want to look at is what is the value of the function? Come on, why won't this work now? What is the value of h of -2? Well, we have that. We know h of -2 is 3. So that means we have to make sure that the left and right-hand limits also equal 3. So what we want to do then is say that the limit as x approaches 2 from the left, let's see what that is. So that would be in that function. So if we go from the left, we would get, put 3 in, or -2 in, we get -4, -9. Hold on, I can't multiply. We get -1. And then if we do the limit from the right, we would get, what do we get here? I don't have it written down. So we would get, it's -2, so that's -8 plus 12 plus 3. So that's 7. So we can say that the limit does not exist. Okay, so then here's what we have. We have that 1, h of -2 equals 3, 2, that the limit as x approaches -2 of h of x does not exist. So therefore, h of x is not continuous. At x equals -2, but continuous at all other values. Okay, and we know that because we have 3 continuous sections. Okay, finally, let's do 6 and 7. Using the 3-part definition of continuity, create a system of equations. Then find the values of a and b so that f of x is continuous for all reals. So this is just like we were doing, but now we have 3 parts instead of 2. So we're looking at the point x equals -1. So the easiest place to start here, because it's a point, is the value of the function. So one thing that we know is that f of -1 is going to equal 6. So now what we can do is we can find our left and right hand limits, knowing that they're 6, and then we can solve for a and b. So what we have then is the limit as x approaches -1 from the left of f of x is going to equal 6, and the limit as x approaches -1 from the right of f of x is going to equal also 6. But yeah, I don't have my computer plugged in, so it went on power save mode. So it got darker, it kind of freaked me out there for a second. So let's go ahead and set up the system of equations then. So what we have is that we have 2ax minus b equals 6. And we have ax squared plus b equals 6. Now what we do know is that x equals -1, so we can get rid of that part of the equation. So we're going to have -2a minus b equals 6, and then we're going to have a plus b equals 6. And now we can solve these. What's nice is it's set up for elimination. So we'll go ahead and do that. So we get -a, b's will cancel, equals 12. So a equals -12. And then if you substitute -12 into this equation, you're going to get that b equals 18. And so we found our answers. There we go. A is -12 and b is 18. So you know that a function value and the limit value can exist independently of each other. Let's summarize the big ideas of continuity on intervals at a point and one-sided limits. So now we're given another piecewise function, and these come up a lot, piecewise functions. G of x equals 2x plus 1 where x is less than 3, and g of x equals x squared when x is greater than or equal to 3. So find each of the following. So the first one is the limit from the left. So that means we're going to use this piece right here. And since it's a line, we can do direct substitution. So the limit as x approaches 3 from the left of 2x plus 1 is just going to equal 2 times 3 plus 1. So this is going to equal 7. The limit from the right, now we're going to use this piece because we're coming from the right. So the limit as x approaches 3 from the right of x squared is just going to be 3 squared. So that's going to equal 9. And then g of 3 is going to be where we have the equal to part. So g of 3 is going to equal 3 squared, which is 9. And so the limit, we're going to have to look at the left-hand and right-hand limit to get the limit of 3. And what we see is that this does not exist because the limit as x approaches 3 from the left is not equal to the limit as x approaches 3 from the right. And is x continuous at 3 justify? Okay, so the answer is g of x is not continuous. At x equals 3, that's important, since, because it is continuous other places, since g of 3, is not equal to the limit as x approaches 3 of g of x, or you could have said the limit does not exist. Either of those answers for justification would have been sufficient. So we're going to end this by saying if a function is continuous at a point, then the function value and the limit value are the same. That's very important. And it's also important that you make sure that you're checking those left and right hand limits. So we're going to do some practice of this. This is a very huge concept in Calc 1.